Example, problem 3 has us looking at K and the reaction quotient. So it gives us the reaction of ammonia, and it gives us the equilibrium constant. So that's what K is at that temperature. We do want to remember that at different temperatures, the K changes. And that's a big thing. Whenever you are changing the temperature, you're going to have a new K. When they give us concentrations, unless they specifically say that those are equilibrium concentrations, when we plug those into our equilibrium expression, we assume those to be the reaction quotient, or Q. So I started by writing my equilibrium expression, products over reactants, coefficients as exponents, paying attention to the states. I did say that I know what K is equal to at the temperature we're at. Then I already have my expression in both of these cases, and then I'm just carefully plugging the numbers into the correct place. And as you do that, make sure that you carry your exponents down. Make sure that you're paying attention to the order of operations in your calculator as you're getting to your final answer. So in this case, we've got a big number. The Q is significantly larger than the K. The Q is in the millions, whereas the K is a decimal. That means we have, relatively speaking, way more products than we would have at equilibrium and way fewer reactants. So in doing that, we shift left, which makes more reactants, meaning that our ammonium will be consumed and our nitrogen and hydrogen will be produced. Those will go up as the other one goes down. Or we could just say shift left, depending if they want mathematical proof, explanation, justification, or both. On the second example, we've got new values. We plug those in, same idea. In this case, at least when we're going to the 2 sig figs, K is equal to Q. That means that even though it didn't tell us that we were at equilibrium, we have proven that these are the values or the relative concentrations that this equilibrium reaction could have at equilibrium. It's possible to reach equilibrium with all sorts of different concentrations, really high, really low, and in between, as long as it comes out to that same value according to the law of mass action, and it does come out to that same value in this case. So we are at equilibrium. We don't need to shift. That does mean that the reaction proceeds. Reactants still turn into products and products into reactants, but we are not having a net change of more products or more reactants.